welcome everyone to today's webinar. I'm really excited to have Dr. Cetin Savkli, who's the chief scientist here at Johns Hopkins Applied Physics Lab, and also an instructor in both the applied math and computational statistics and computer science departments at Johns Hopkins University. Speak today. Especially because this is a topic that I've gotten a lot of interest in on graph analytics. So right when I heard a lot of feedback from the last seminar that people would want to hear about graph analytics, I knew just the person to ask, because he's spent a lot of his time here at APL developing new algorithms for probabilistic modeling of high dimensional data and large scale graph analytics. So I knew that his talk would fold in nicely today. So I'm really excited. Just one thing I wanted to mention before we get started. You can contact me if you're interested in a future webinar, or you can go check out our community website here, just community.amstat.org, and go to SDNS. I also wanted to make one more plug for DataWorks in April. That's a conference that the Section on Defense and National Security co-sponsors with IDA and NASA. And there's a lot of good talks there and tutorials and webinars. So please go check it out. So I'll stop sharing and we'll hand it over to Dr. Savkli to get started.
Thank you so much for the invitation, Joe, and thanks to everybody for dialing in, taking time to attend this. I hope it will be worth your time. This will be like an overture to a class I have created to cover this topic as well as I can. Based on a need about 10 years ago, I do my job, we have new employees always, and we were finding out that people were coming with various skill sets, but there wasn't a class suitable to cover all of the things that were relevant for graph analytics. So this class was a result of a need, basically. And graph analytics is about half of what I do, but it accounts for about all of the questions I get usually, which shows, I think, the interest in graph analytics. And it's a fascinating field that combines a variety of interesting topics on their own, things like linear algebra, probability and statistics, and computer science. So there is definitely, it's at the intersection of lots of interesting problems. And I'm going to go over a few of the sort of highlights of interesting topics. I tried to cover different areas of it to give you an idea about what kind of things graph analytics involve. As you can imagine, given the limited time, I had to make some choices. So this is far from, of course, complete, but it gives you an idea. So graphs go back to 18th century. The first, graph theory, start of graph theory is attributed to this problem of Königsberg bridges, which is currently called Kaliningrad in Baltic Sea. It's part of Russia currently. But at the time, in 18th century, townspeople, when they go out walking, there was this question about, can you cross all of the bridges? The town had these 7 bridges. Can you cross all of the bridges without crossing any bridge more than once? That was something they kind of thought about. And Euler was the person who answered this negatively, that it was not possible. And it follows from the fact that if you don't cross any bridges, by the way, I didn't mention, but this is the network representation of this connectivity of these bridges and the landmasses, basically. These are 2 islands, which are represented by these 2 nodes, and the other 2 landmasses are represented by these 2 nodes, and links are corresponding to the bridges here. So in order for there to be a solution, you would have to, for the nodes that are along the path, you would have to go in and come out. So you have to have even number of links. So only two nodes in the network are allowed to have odd number of links. Those are the start and end points. And unfortunately, in this network, as you can see, these are all odd number of links. So it's not possible to traverse all these bridges without crossing a bridge more than once. In the Second World War, it was actually two of them were bombed by Germans. So the problem became temporarily resolved. But again, the problem was the starting and end points had to be these two islands, which is not ideal for most people, I guess. Fast forward to our current era. As you all are aware, networks are everywhere. Some of them are more obvious than others. Social networks clearly is what people think of when we think of networks mostly. But there are networks in other domains, which is, and this fascinates me more than the obvious networks, how networks pop up in places where you wouldn't think of networks naturally. For example, disease and gene network, where nodes can represent diseases and genes. As you can imagine, this can be a very large scale network because humans have a lot of genetic data. And analysis of such networks, for example, can be useful to identify relationships between diseases and between genes also, and potentially figure out what drug, for example, can work with for what disease. So there's a rich possibility of questions you can answer. And scientific literature is another network because papers cite each other's. Actually, patents are also a network. Patents refer to other patents often. And I won't go into too much detail of this type of analysis, but I can quickly mention that we've done, in response to a challenge a few years ago, we've done this patent analysis to predict future important patents. And we were provided data set from government that corresponds to the last 30 years or so of patents. Using various graph centrality metrics, we were able to correctly identify what patents would be most important in the future. Of course, we had to separate the data into past and future, but some of the graph metrics have been used in these domains with very interesting results. And some of those centrality metrics I'm going to talk about and will remind you at the time. Supreme Court cases, again, refer to each other, so that's a network. And some of the maybe less sort of obvious applications of networks are on this slide. For example, logistics and flow analysis. This is an analysis that, for example, looks at the flow of traffic between different points in the United States. And there are metrics we can use to do such analysis. And document analysis is another area which we don't always think of it as a graph problem, but as you can imagine, you can represent documents by the keywords, the characteristic words that you encounter in those documents, which can be defined according to various statistical metrics. And once you do that, you suddenly have this bipartite network of two different node types where documents and keywords are linked to each other. And from this, as you can imagine, you can infer relationships between documents. Not only that, you can infer relationships between keywords also. And some of the lesser sort of known applications of graphs are in the field of clustering, particularly when it applies to clustering of topologically complex data sets. And I will talk about that in some depth. And probabilistic graphical models are another area where graphs become handy. And probabilistic graphical models address the question of, if you have data, attribute-rich data, how do you build a probability model that captures the relationships? And some of the graph algorithms are relevant for this purpose. And there is yet one more important use of graphs. In fact, this is what started for me. My exploration of the graph started about a little bit more than 10 years ago with this particular problem that we had at Johns Hopkins Applied Physics Laboratory, that a sponsor had a very complex data set that involved many databases at different sites. And the question was how to do seamless analysis of all this data. The first question was how do you even bring this data together? And it was a very complex process. Just to understand the structure of the data took us close to a year. And at that point, it became clear that organization of the data and how you represent the data, how you make it available is a very important decision, and it can enhance your ability to analyze, or it can hinder your ability to analyze data. So we have started looking into a graph way of looking at the world at that point. And humans are sort of driven to represent knowledge by nodes and links. When you draw something on a whiteboard, typically you put some dots and some lines connecting them. So it's a very common, very visually sort of understandable way to represent knowledge. Here, for example, I have, just for illustration, represented different modalities of data where these people are, for example, taking these flights, where the link indicates that this person was on this flight, and then this link indicates that there's a wire transfer between these individuals, and this link indicates these two individuals live at this address, etc. And you may have businesses, ships, and ports, other information. As you can see, although these data are all different modalities and typically it may reside in different databases, on a graph they can happily coexist. So that is a great feature of graphs, how organically you can incorporate new information. And so I won't say too much more about this, but this is one of the big reasons why sort of I have gone into graphs. And there's a lot more to say here, although I'm not going to focus on this aspect of the work regarding scalability of how we do this. And there are interfaces and different storage backends. This goes into a little bit more software and computer science side of graph analytics. So I'm going to leave it at that, but please get in touch with me if you would like any references or sort of tips about what you can look into if you have worries about how to do scalable, sort of large-scale data management using graphs. So the types of analysis involving graphs are, modeling graphs is a big area of analysis because our ability, our confidence in how well we understand graphs can be measured by how good we can model it. Just like in any other physical kind of problem, if you are able to model graphs and capture the characteristics of real-world graphs, that's a good sign that we understand the characteristics of those graphs. And identification of communities, measuring importance of graph elements such as nodes and links, and there's a rich set of metrics that measure how important nodes and links are, depending on what question you are interested in. For example, resiliency is one example. And link inference is a big area of interest, given what we know about data. Can we infer additional links? This is something everybody is, I'm sure, familiar from social networks, such as Facebook or LinkedIn, for example, where you would be recommended people to connect with. Those are forms of link inference. And in the example of document indexing, again, understanding relationships between documents, that would be a form of link inference also. And also understanding processes such as contagion or diffusion or propagation of things on graphs. It could be diffusion of ideas even. That's an area of graph analytics. And there are mathematical methods that rely on graphs, as I already mentioned, things like probabilistic graphical models and applications to clustering. All right. So the structure of the graph is essentially can be captured in the form of a matrix. This is the most elementary way to represent it. And graphs can be directed or undirected. And there are different ways of representing this information in the form of either adjacency list or edge list. So these two are about how we want to manage this information so that we can quickly get the sort of information back. And these are pros and cons. Essentially, adjacency list gives for every node, it gives what other nodes it links to. Here, there are two sets, as you can see, because of outgoing and incoming links. So you can quickly look up, for example, for node number 2, we have 3 and 4, which are these two. So node number 2 points to 3 and 4, and 5 points to 2, and that's this link. And the edge list simply gives you a list of edges. For the adjacency list, it's more work to lookups are very fast for the neighbors, but it's more work to figure out if two nodes are connected. And in the case of edge list, it's easy to check if two nodes are connected. However, it may be more work to look up neighbors of a node. You would have to parse multiple rows. Of course, links often have weights, which may indicate strength of relationships, and matrix representation can accommodate that. We can have weights as entries of matrices. So how these weights are used is algorithm specific, but matrix representation can easily allow you to do that. Networks are not always homogeneous, as we already saw in the cartoon example earlier. There can be different node types, and these are some examples. For example, movies and users. Which users like which movies? My video. Which users have seen which movies? For example, this is a bipartite network, and similarly in the cyber domain, you can have email communication, for example. Because email communication can be one-to-many, in this case, it is not desirable to represent email communication as a homogeneous network, because then links, it would be, endpoint is not a single user. So it would have to have a structure that is a little bit more complicated than just a homogeneous network. And this is one way to handle that. In fact, the structure of the network, that decision is a subjective decision. And there are many ways to construct network structure. Imagine just a table. For example, email records are an example. Emails can be represented in a table where each row is one email, basically, with some columns like the names of recipients, etc. So there are many columns, and if you think about how to divide this information into a triplet, let's say we are trying to construct a node link node type of graph. There are many combinations there. N factorial, if you divide that n attributes into 3 sets, there are many combinations to do that. So graph structure on its own is a fairly interesting topic. How do you decide what structure is optimal? Often we use human sort of insights in deciding what would make sense. So statistical property is the most elementary example of statistical property is node degrees. And node degree describes how connected each node is. And you can define out degrees and in degrees. Out degrees indicate how many other people or nodes a given node points to. And here I'm going to use some linear algebra language because I hope you will appreciate how elegant linear algebra is to work with graphs. I always find it interesting that there are very concise implementations, linear algebra-based implementations of many graph algorithms. Admittedly, degree is a simple calculation, but think of the following. If you were to calculating degree, you would have to write a for loop, essentially go over all vertices and check how many links they have, and essentially do this aggregation. As opposed to that, when you are doing linear algebra, that operation it can be done in one line, essentially with just a matrix multiplication of this simple vector of just ones with the adjacency matrix. If you multiply from the left, it sums out the first index, which gives you the outgoing out degree. And if you multiply from the right, it gives you in degree. So its implementations can be very simple if you use adjacency matrices. And so the directionality may be important in some problems. Often we use undirected links, but degree has some limitations, of course. It tells you very local information. Here, for example, these vertices all have degree 2, so they are equally important as far as degree centrality is concerned, but that may not always be the case, and we will see a better metric shortly. Another characteristic of another way to describe networks is how this degree is distributed over the entire network. And networks may have exponential or scale-free degree distributions. These are broadly two types of networks that you may encounter. And we call these long-tail distributions, and they go as 1 over some k to the alpha, where k is the degree. So long-tail distributions are encountered very often, especially in real-world networks, such as social networks, for example, have long tails. You will have people with thousands of connections, for example. As opposed to that, in the random networks, variance is much lower. So in a random network, node degrees are highly localized. As you can see here, no node is very different than other nodes. They are more or less the same. Some have 1, some have 3 links, and most has 2, etc. But here you have some nodes that are very high degree and some nodes low degree. So this is, and this forms the basis of 2 different random network models that I will briefly talk about. The first one is Erdős-Rényi model. This is the most basic random network model. It solely depends on the assumption that average degree in the network is lambda, or equivalently, probability of connection between 2 nodes is given by p, which is a function of lambda. So you can specify the network by either one of these parameters as they are related to each other, where n is the number of nodes in the network. So this assumption leads to a binomial degree distribution, which in the limit of low probability gives us the Poisson degree distribution, and this is the non-long tail distribution. Erdős-Rényi model has been studied often. It's a simple model. It allows us to explore some interesting concepts. However, if you look at the scaling properties of real-world networks, this is from a paper by Albert and Barabashi, where gamma out and gamma in are the powers of this 1 over k distribution. So as you can see, these are mostly long tail distributions, most of the real world networks. And so essentially, a long tail is a very common characteristic we encounter. And because of this, another model was developed called Barabashi-Albert, and this is a preferential attachment model. I won't go through the whole derivation here, but the derivation essentially, this is a hint of how it goes. The attachment probability, if you have a community of people like Facebook, let's say, where everybody has certain relationships, when a new member comes, according to Barabashi-Albert model, probability of you attaching yourself to making friends with one of those people is proportional to the degree of existing nodes on the network. If you make that assumption, essentially, and allow some random connection also, where P is the probability of making some random attachment. Essentially, if you set P is equal to 0, all attachments will be preferential based on the degree of the existing neighbors. So this is a free parameter that can be set to 0 to make it purely preferential. But making this, defining this model gives us an equation. This is, as you can see, like a differential equation about how much the degrees of existing members will change over time. So, and you can solve this equation, and it gives the following result. Essentially, it is doable analytically. It gives a degree distribution that goes as k to the power minus 3 minus p over 1 minus p, where p is the probability of making a random attachment as opposed to preferential attachment. So if you set p equals to 0, it becomes purely preferential. As you can see, you get long tail degree distribution. And if you let p goes to 1, that means all connections will be through random attachment. The result reduces to essentially Erdos-Renier result, where it is heavily suppressed. So high degrees will be heavily suppressed. So those are the two dominant models that you will encounter in modeling, random graph modeling. So one of the fascinating things about this degree distribution is how we perceive ourselves in the network. I don't know about you, but when I look at networks that I'm in, it feels like everybody else has more kind of connections than I do. So, and that it turns out that's a phenomena that there's nothing really necessarily wrong with anybody, but that's how the math works. And this analysis kind of illustrates that. So the question is, what's the probability that a random link is attached to a node that has k links? So so the probability that you attach yourself to somebody who has k links, imagine a network where everybody has half links, let's say, and everybody's degree is set. Like some people have 1,000 links, some people have 5 links. Imagine an existing network. And if you cut all these links into half links, and then if you ask the question of where does this half link endpoint go to? Well, the probability that that half link endpoint is attached to somebody that has k links is proportional to number of links that belong to people with k links have. So so this can be calculated. Essentially, this expression, number of people, number of links people with k links has, is given by distribution of probability distribution for that is given by k times p of k, where p of k is the degree distribution of the network. So so therefore, while the graph degree distribution is given by p of k, degree distribution for your neighbors is given by k times p of k. So it's a different distribution than the overall degree distribution. And I'm going to show this with a simple example where it will be very clear. But if you are wondering what the average degree of your neighbors are, or any node's neighbors are, we can calculate that average using this neighbors degree distribution. And that gives us this additional factor of k. So essentially, it is like k squared average here. So the mean degree of the overall network is k, and therefore the overall average degree of our neighbors is given by mu squared plus sigma squared over mu, basically because it comes from this expression that you see here, where k squared is this term and k average is the denominator. And instead of k squared here, I have simply replaced, using the definition of standard deviation, I replaced this k squared by mu squared plus sigma squared. So this is an interesting result that your neighbor's degree distribution is actually higher than the average degree over overall network. Basically, as long as the degree distribution of the network has a standard deviation that's not 0, you will always have, if you ask people across the network, their average degree of their neighbors is going to be higher than the average degree of the network. So here's an example of that. This is a simple network where everybody almost has 3 degrees except the central node that has degree 6, and average degree on this network is 3.43. But if we ask these nodes on the periphery what the average degree of their neighbors are, you see that here average degree is 3.3, 3 plus 3 plus 6, so 12 divided by 3, that's 4. So everybody on the periphery will tell you that on the average their neighbors have degree 4. And so essentially most of the nodes have a skewed view of the network because of this high degree node. And this becomes only worse when the network has a long tail, basically. The longer the tail, the worse this behavior gets. So most nodes will have this view that they are less popular than people they are connected to, which is a result of this long tail distribution. There's one other thing that involves degrees that's interesting. That is the degree correlations. If you take a network and calculate degree correlations between the endpoints of links, which can be done using the matrix representation, as you can see here, degree correlation can be calculated essentially by calculating these four quantities. And they can all be calculated very easily. This one in terms of the adjacency matrix, and the correlation is given in terms of those. So networks can be disassortative, neutral, such as random networks, and they may be assortative also, where there is a degree correlation. Disassortative network examples are cyber and biological networks, and assortative examples are social networks. It turns out assortativity is important for resiliency. This is an example that shows that. In the left side experiment, we have an assortative, that is a network. These two networks were built in the same way in terms of degree distribution, except the left network was rewired to make high degree nodes connect to each other so that there's degree correlation. Whereas the network on the right does not have that. It has assortativity of -1. So after removing the top 30 high degree nodes, and this is a type of targeted attack, for example, what you are seeing here is red nodes are the largest connected component of this network. So after removing top 30 high degree nodes, we still have a network that is highly connected. There's a large chunk of the network that's highly connected. If you look at the right network, after removing only top 10 high degree nodes, the network is largely destroyed. As you can see, there's a large island of disconnected parts in the network. So this is an interesting illustration of how certain characteristics of networks can play a role in resiliency of that network. And assortativity is one of those characteristics. Another behavior that we observe is a behavior of sudden change in networks. Interestingly, as simple as Erdős-Rényi model is, Erdős-Rényi model displays a sudden change. Sudden change is clearly of interest. We often see social phenomena. When we talk about, for example, on Twitter, suddenly everybody talking about something. This happens only sometimes. Sometimes everybody talks about the same thing. Sometimes something that you would think is unimportant can become a big thing that suddenly the whole network talks about. Or sometimes very important topics may not be talked about. And this can happen very suddenly, and it's hard to predict these kind of things. So sudden change is of interest in networks. And what is the mechanism that causes that? And Erdős-Rényi model, as simple as it is, provides a hint of how this can work. And I'm going to show you the way this happens. So the phase transition in this case, which is the sudden change, happens as a function of the average degree in the network. What you see here as described as S is the size of the largest connected component in this network. So as you see here in this network, the red nodes represent the largest connected component. In this network, they represent about maybe 70% of this network. So that S is that variable that tells us how big is the largest connected component. What happens in Erdős-Rényi network is, as you start increasing the average degree of the network, which you can do by slowly adding more links to the network, the largest connected component size stays very low for a long time until you reach the average degree of 1. After you reach the average degree of 1, if you continue increasing the average degree, something very dramatic happens. The size of the largest connected component goes up very rapidly. And when you reach to even 1.5, as you can see, most of the network becomes connected. Nothing until 1, there is no sign of any large islands on the network. But if you add half more links on the average per vertex, suddenly most of the graph is connected. This is an interesting phenomena, and it's observed. The way it works is essentially what defines this connected size of the connected component is provided by an equation of this type, derivation of which I'm going to skip, but if you're interested, it's you can find it in the references that I provide at the end of these lectures. But giant component size is provided by this equation that has size of the component both in this exponent as well as on the left-hand side. So solution of this equation depends on lambda, where lambda is the average degree. So what happens is when lambda is very low, essentially two sides of this equation, which is the straight line, and this curve, which represents the right-hand side, do not intersect anywhere other than 0. For low values of lambda, for example, what's the lowest value of lambda here? It is 0.7. When lambda is 0.7, you have right-hand side is like this, and the straight line is this. And as you can see, intersection is at the origin. When lambda is equal to 0.9, now we get the second curve. There is still no intersection. Solution for the giant component is still at 0. So there is really no large islands in the network. And you increase it to 1.1, that is this curve, then intersection is still fairly at a low value. But you see what happens around the value of 1.2, 1.3, we suddenly start, this curve starts intersecting at very rapidly. This point of intersection, there's a non-trivial intersection. There's still a 0 intersection here, but there is a non-trivial intersection way out on the higher values of S. So this is how the behavior is observed and giant component is formed. Same thing can be observed also in this lattice percolation problem. Lattice percolation problem is essentially you have this lattice, and this can be a site or bond lattice, where the lattice can be defined based on sites being on or off, or links being on or off. Imagine like a grid, basically, of links. So there are two versions of this problem, site and bond percolation. I'm here showing site percolation. The red cells mean those cells are on. Dark cells mean they are on, gray or red, that means they are on. Red cells are the largest connected component of this on cells, basically. This is very much like a network, except the links are local here. Every node here is represented by a cell, and the links are, if two cells are on, that means there's a link between those two cells and they are connected. As you can see in the simulation, as p approaches 0.6 here, which is p is the probability of a cell being on. And you can imagine that this corresponds a little bit to the previous result, because every node will have 4 neighbors, and if p is 0.6 is where the threshold is, and imagine 4 potential neighbors, when p is equal to 0.6, so you will have about 2 or so neighbors for a cell that's on, basically. So it's so there's a correspondence between this probability of a cell being on and the average degree in the network. So and derivation of this is it has been actually studied for a long time. In fact, it predates most of the graph analytics research. And here there's a sort of toy derivation of it that I have played with. But for a more detailed derivation, you should refer to this paper by Kesten, the critical probability of bond percolation on a square lattice. This is, as you can see, it goes back to 1980. And apparently, this problem was studied for a long time, and it was unsolved for a long time, which is quite interesting. And in this case, for example, Q here is the probability of a cell not being part of the giant component. So probability that a cell not being giant component can happen in one of two ways. Either the cell is off, which is given by 1 minus p, or the cell is on, but the neighbors are not part of the giant component. This is not strictly accurate because it assumes independence about the neighbors not being part of the giant component. But I like this because although it is not exact, it's a very quick way to see actually how all this giant component formation works. And this equation is exactly what's plotted here, just similar to the previous plot for the Erdős-Rényi model. Here I plotted this Q and the right-hand side for to illustrate the same behavior essentially. And in this case, P is equal to 0.54 is what I came up with. And as you can see in the simulation, this simulation gets 0.6. But there are boundary effects, etc. So because this is a finite lattice. Anyway, the reference is here for those interested in percolation. So this is an area that has relationship to essentially phase transitions and networks. It's a type of it's a type of network essentially where the links are more local. And next, I want to talk a little bit about community structure. Community structure, the previous models that we talked about has not really said anything about the community structure. It was mostly about degree distribution and whether it's long-tailed or not, etc. But most social networks have community structure, which is defined often by triangles. However, a quick back-of-the-envelope analysis indicates that triangles are very rare. Probability of 3 random vertices, for example, forming a triangle in the Erdős-Rényi graph is just lambda over n minus 1 to the q, because this is the probability of connection between any two nodes. And this is a very low number, of course, but there are many triplets, so n pick 3. However, even with that, n pick 3 is, there are combinations, triplets, n pick 3 triplets in the network. How many triplets there are? This is on the order of n cubed. So n cubed divided by n cubed, those cancel each other. And we have this interesting result that on Erdős-Rényi networks, number of triangles actually doesn't depend on the number of nodes in the network. That's quite interesting. And it tells us that number of triangles are very difficult to achieve on a random network. So if you generate networks randomly, you are not going to get many triangles. And this relates to the metric of clustering. So the clustering coefficient measures how triangulated a network is. And typically, for example, for this node, and clustering coefficient can be defined both for nodes as well as for the entire network. For a node, clustering coefficient is defined as, if you look at all the neighbors of a node, what proportion of those neighbors, what proportion of the possible links between those neighbors exist. For example, here, every node has 1, 2, 6 neighbors. So there are 6 pick 2 possible links between those neighbors. If I look at these 6 neighbors, there are 6 pick 2 possible links. But how many actual links there are between them? There are only 6 links between them. Although this network looks like it's very highly clustered, and it is fairly highly clustered, when you calculate the clustering coefficient, you get 6 over 6 pick 2, which is 0.4. So it's far from being perfect. But still, this is a very high number. As opposed to that, for Erdős-Rényi network, clustering coefficient is much lower because it's given by lambda over n essentially, because that's the proportion of the links will be there basically, since this is the link probability, and this proportion of the potential links will be observed. So this is almost 0 for Erdős-Rényi networks. Clustering coefficient is almost 0, and real world networks have very high clustering coefficient. Here you can see the comparison of clustering coefficient, for example, for a random network that has the same kind of degree distribution, let's say, for this actual data set. the clustering coefficient of the actual data has very high clustering, whereas the random networks are very low numbers here. As you can see, there are orders of magnitude differences. So that's kind of an important feature to capture if you model networks. And what Strogat's model attempts to address this, and the way what Strogat's model is built is by starting with a highly clustered network and randomly rewiring it. So this gives you a network that has very high clustering, and so this is one way to get the high clustering aspect. And also you can accomplish short path lengths, because every time you rewire, for example, if you rewire one of these links to cross this circle, then suddenly longest distances will be halved immediately as a result of a single rewiring. So it's possible to get short path lengths, which are characteristics of social networks, while having high clustering. And that's the desirable region, where here you are essentially trying to accomplish high clustering and short path lengths. And what Strogat's model accomplishes that. And the missing feature here is you still don't get the long tail degree distribution. But these are just some of the random models, the random network models. There are other models with more features. Here, I just wanted to show these three only. And another interesting point about the real world networks is the way the connections are. Not only it's highly clustered, but also connections are, they follow certain distributions, which are really interesting. And this was an experiment done in 1967, which is quite remarkable, and done by an experimental psychologist, Stanley Milgram. Milgram wondered if he gives these 96 packages to a group of randomly selected people in Omaha with instructions to get these packages to this destination, who was a friend of Milgram, by following the following rule, where each person can only send the package to somebody they know personally. And they know where the destination is, but they don't know, so they don't know the address of the specific person who's going to receive the package, but they know where the destination is, but you can only send it to somebody you already know. So this experiment was done in 1968, and only 18 packages reached the destination out of 96 or so. And interesting point was average hop length was about 6. And this is the origin of the popular notion of 6 degrees of separation. So average hop length being 6 is quite interesting. So Milgram's experiment demonstrated 2 things: that short paths are in abundance in a large-scale social network, and people acting without any global knowledge of the network, other than knowing their immediate links, they are effective at collectively finding these short paths. And this is quite interesting, because when we are doing these kind of analysis on a computer, and we find shortest paths, there is a lot of iterations. There is a search usually, such as depth first search, for example, looking for the optimal path. So you have to do a lot of backtracking, going back and forward. And so there's a lot of sort of failed routes, but people didn't have this luxury in this experiment. You just mail the letter and that's it. It basically goes. And despite of that, and it was remarkably successful that so many of these letters found the destination in so few steps, such as 6 hops only. So this was studied, and there's so Kleinberg, it was studied by Kleinberg, who has a very good book for those interested in this graph analytics topic that I highly recommend. It turns out not only people have long distance links as well as lots of short distance links, but these links are distributed according to a certain distribution where this kind of operation can be optimized. So the distribution of links, if it is over 1 over x squared, then this gives us the optimal result for making things reach to a destination in the fewest number of steps, because essentially what this does is it gives us equal reach at different scales. So how did society end up with this kind of connectivity is an interesting topic, but clearly there is an advantage to have connections according to this distribution in terms of quickly reaching to sort of any point on the network. And this is an experiment done, and the reference is provided here, and it demonstrates through simulations that the optimal power of this distribution is around 1 over r squared kind of distribution. Yeah, this is something quite fascinating, that human society is organized like that. And community finding is one of the important analytic questions often when we have large-scale networks. Our question is, who are the tight-knit sort of groups in this network? And there are different ways of doing that. I will start by showing the most elementary type of community, that's the graph components. Those are connected sets of nodes. For example, in this toy graph, there are 2 components, and component finding can be done in a variety of ways. This is a linear algebra-based way. Essentially, what you can do is you can look at walks, what we call walks. Walks are starting from a node I. You traverse the graph by taking a certain number of hops. For example, if you look at a squared, ij element of a squared gives us all the ways you can go from I to j. And this is essentially going through intermediate nodes L. So the a squared ij will tell you, for example, for this network, the result will be exactly 5, for example. So if you look at an adjacency matrix and then calculate a squared, a cubed, these will give you how many ways you can go from I to j in 1 hop, in 2 hops, in 3 hops, etc. And if you take union of these results using the definition of this union, where if either entry is non-zero, the result is 1, otherwise it's 0. So that basically says if there is at least a path from I to j in 1 hop, 2 hop, or 3 hop, or k hops, then that entry will be 1. And as you can see here, when you do that, even second order, you get a matrix structure that's like this. You see these blocks, so you can readily identify the components of this matrix. This is a very simple one, but it works on larger matrices also. And there are more efficient ways of doing this using, for example, matrix inversion, which is an equivalent way to doing this calculation, this union. Instead of this union, which you have to truncate at certain k, you can do, for example, matrix inversion by picking a small alpha for numerical stability. So if matrix cannot be inverted, again, you can revert back to iteration. But typically, most real-world networks do not require more than 3-4 hops to go from any node to any other node. Therefore, you often don't need to go to the high-order terms here. Well, components are not terribly interesting, although it's the first thing we typically find. Cliques are somewhat interesting, but they are highly connected communities, and they are very restricted. Clique is defined as follows. Every pair in a clique has a direct connection between each other. So this makes cliques very fragile. Here's an example. In this set of nodes, we would almost have a clique if we had this link also. But just because we don't have this link, this would disqualify as a clique. So you would have to have all possible relationships in this network. So while cliques are, they seem like perfect sort of community, they are rarely observed in the real world, and they are not particularly useful. And clique finding is also computationally one of the hard problems called NP-complete problems. So you don't want to be looking for cliques on large-scale graphs. Often it will be not a very fruitful activity. This is my favorite community finding approach that I highly recommend. It is called trusses. and trust finding is evidence-based link evaluation. So in trust finding, we accept or reject links based on how much support they have. So if the rule is very simple. A link is accepted if it is supported by at least k joint neighbors. So and that is k can be anything. So we decide what k is. And what's the idea behind trust finding? Well, the idea is, as you saw, for ergothree graph, triangles are very rare. So it's very difficult to find triangles. And what you see here is, so if you have triangles, that's very valuable, basically. So in real-world networks, triangle provides a lot of information about relationships. So if two individuals have other supporting relationships, joint associates, then that makes this link more believable. Sometimes, for example, you may get a connection request on LinkedIn from somebody you don't immediately recognize. If you look at this person and you have nobody in common with the person, I'm sure most of you would just decline that request. So because not having common associates at least is a good sort of reason to decline that link. So how do we do trust finding? There are different ways you can implement this. Essentially, one way is you can again use this path idea where A squared tells you how many joint associates these two endpoints have. So A squared can be very useful for trust finding. What you can do is, while there are potential edges to delete in your network, you can update A squared, and for each remaining edge, which you can get from the adjacency matrix, if A squared ij is less than k, then you set aij equals 0. So whole implementation can be as simple as that. This is not the fastest implementation, but this is all basically there is. Until there is nothing more to be deleted, you can repeat this loop, and you check A squared value, and then set aij equals to 0, and then update A squared and check A squared values. If anyone is less than k, set it equal to 0. So anyway, that basically gives you the trusses at the end to degree k. A better way to do it is building this triangle edge graph, and this is a faster way to implement it. Basically, in this network, every triangle is represented by a node, and every edge is represented by a node. Once you build this network, then finding trusses become just a matter of iteratively deleting things until there's nothing more to delete. You don't have to continually find triangles. You don't have to worry about the calculation of the A squared matrix over and over, which is a costly operation. In this case, finding trusses become a simple matter of deleting things. You iteratively delete edges with degree less than k and triangles with degree less than 3. Because if a triangle is less than 3 degree, that means it doesn't have enough edges that support it. So this can be very fast compared to the previous algorithm. And here I have created an example for you to see. For example, for this network, initial edge triangle network would look like this. For example, 2 is this link. 2 is part of this triangle, for example, and as well as this triangle and this triangle. So it's part of these 3 triangles. That's why it has 3 links, and so on. So when you build this network, you can immediately see certain edges do not have, for example, if you are trying to find 2 trusses where we require every edge to be supported by 2 triangles, we will immediately delete these white boxes, because these boxes, these are the edges that are only supported by a single triangle. So I would go ahead and delete these edges. Once you delete these edges, the network, you would then delete triangles. For example, this triangle would have to be deleted as well, because once you delete this edge, this triangle now has only 2 edges left. So we delete that as well. So all of these dash connections and the associated triangles and edges will be deleted. And essentially, you will be left with these 2 islands. And those are the 2 trusses on this network. So I can, I'd like to actually quickly show you that here. And here's a students network. This is a group of students in 2 United States schools. if you look at the trusses in this network at low level, for example, this link is not supported by any triangle. So I don't expect this link to survive part of being a truss. So as you can see, that link has disappeared. All the remaining links are part of at least one triangles. If I want to be more restrictive, I go to two triangles. So what you see on this network is all the links that are supported by at least two triangles and three triangles. And actually, what's interesting here is these students belong to different grades in the school. And if you look at the, let's see, node icons by grade, for example, you see that these icons, although they are not really distinguishable, yeah, because, okay, let's make one of them triangle. I guess I don't have enough icons to represent different grades. But as you can see, these are all circles, for example, blue ones. But the algorithm really doesn't know about the grade. And these are all squares, and these are all heptagons or something like octagons. And there is some mixed also clusters here. And so trust finding can find these meaningful communities. And finally, these are the most tight-knit groups of students in the network. What I like about this is it's very similar to almost analysis of a mountain range or analysis of a point cloud data where you identify these dense regions. I view these high trust clusters to be like the mountain peaks, where these are the most tightly knit groups of people. If you consider this network as a terrain, and these high degree trust areas are like high altitude cross sections of this terrain. If you take a mountain range and if you cut the mountain range at a low altitude, you will have this big landmass. But if you cut it at a higher altitude, you are going to have start seeing these islands of various peaks of mountains, and finally you will see the highest peaks basically. The good thing about the trust finding algorithm is it's very fast and it can be run on any size graph. So it's typically my first algorithm to use to analyze the community structure in networks, and it can be very helpful to understand sort of relationships in the network. And a related thing is trapezies. I won't spend too much time on this because it's very similar to the trust idea. Here, the need for trapezies, what I want to say is some networks do not have triangles and cannot possibly have triangles. And one example is a network of people checking into locations. And this is a very common thing. In most bipartite networks, you will not have triangles. So here is a person checking into a location, another person checking into a location. In this network, you will never have triangles. You will have, let's see. Okay. So you can only have rectangles, but everything we have talked about trusses can apply to rectangles instead of triangles. So here we take this each link and we look at how many rectangles that link is part of. So that's how we base the logic of trapezium finding. And as you can see on the students graph, again, we can find communities. So for the students graph, both trust finding and trapezium finding can work. And it's interesting to look at how they relate to each other. There is some correlation, as you can see this from the students graph. The number of trusses and number of trapeziums, once you calculate for each link, how many trusses and trapeziums links support, there is clearly some correlation. However, it's not a given that, it's not a, I mean, it's not a perfect correlation. So there are exceptions. Some links are supported by more trusses and trapeziums, etc. But there is some correlation between the two, as you would expect. And we did some extension of this, I think for the sake of time, since I don't have too much time, I'm going to skip over this link cohesion. We have a paper, it's cited here for those interested in this trust finding, we extended this concept. I will let you review that and say a few things about the centrality. As we mentioned earlier, degree centrality really is not aware of the overall location of the node in the network. So it has limited value. So how many links you have is a very, very limited perspective to how important somebody is. Eigenvector centrality addresses this by looking at not only what your connections are, but how connected the people you are connected are. So it does a weighted average of your neighbors' degrees to define your degree. So you can think of degree as a number of one-hop paths, and you can generalize that concept to number of two-hop paths, for example, or number of three-hop paths. Essentially, eigenvector centrality is that number of higher order paths, basically, because that now becomes aware of your overall position in the network. And here's an example that compares the degree centrality with the eigenvector centrality. In this network, for example, while these three nodes all have degree 2, when we calculate the eigenvector centrality, you can see that while 4 and 6 have equal centralities, 2 has a lower centrality. The reason 2 has a lower centrality is because it's more on the periphery of the network. This is a wonderful result because it shows that eigenvector centrality not only takes into account the degree, but also it's aware of the position of the node in the network. And you can see that also in the students network. I have, I believe, captured the result. Here, the node colors and sizes are based on the eigenvector centrality. As you can see, students positioned in central locations in the middle of the communities or subgroups are, they have high eigenvector centralities. One other centrality type is betweenness centrality, and this is a measure of how often a node is on the shortest path. The reason this node has betweenness value of 9 is because there are 3 nodes here, 3 here. There are 9 possible paths that has to cross over this 9. And as opposed to that, for example, this node has betweenness value of 8 because there are 2 nodes on this side and there are 4 here. So there are 2 times 4 possible paths that go over this node. So it's a measure of how much do you need to rely on a node to be on the shortest path. And on the students network, these are the highest betweenness links and nodes, for example. As you can see, those are not necessarily community leaders, which will be more like in these areas, but they are bridge nodes and links. And these are important, it's important information. When you calculate betweenness, you are essentially finding people who are the gatekeepers kind of to communities. And this has all kinds of applications in, diffusion of information, even in marketing, for example, strategically, offering free products to people, with high betweenness, for example, or if you are trying to convince a village to vote for a given politician, if you market your ideas to the, high betweenness person in that village, you will have a better shot. So these high centrality, betweenness centrality nodes and links are very important also for resiliency of the network. If you are going to attack a network, well, the best way to destroy the network is attacking these high betweenness centrality nodes and links. So it's not necessarily high degree nodes and links, but high centrality, high betweenness centrality nodes and links. We've done this analysis by taking the link weights into account. I'm just providing this result because it shows that link weights can be very important. In the original analysis, we ignored the link weights, but when we incorporate link weights, suddenly meaning of links had a big impact on who is important in betweenness. And obviously, in an email network, if you get 100 emails from somebody but never respond, it indicates that that connection is very meaningless, essentially. I mean, in terms of being a close association. But as opposed to having even 5 emails from somebody and you respond all 5 times, that's a stronger association than a one-sided communication. So those kind of information has to be incorporated into the analysis. Otherwise, you may end up with results like here, where Outlook team and technology Enron turn out to be some of the most important nodes in the network, which clearly those are some distribution services. Whereas when we take the link weights into account, we suddenly see that very meaningful people show up on the top of this ranking. Things like people like vice president, senior vice president, and director. Besides link weights, you can also incorporate node weights into the analysis. In this analysis, I've obtained the data from US Census and built this county network of United States, and also incorporated the populations on each node. So these county populations are part of the node attributes. I have leveraged that information to create a betweenness centrality measure by taking into account the node populations. So probability of somebody traveling from New York to Los Angeles, for example, here I am assumed is proportional to population of Los Angeles divided by the whole population in the United States. And just solely based on that assumption, I was able to capture most of the major road networks. This is without using any actual traffic data, just basically using endpoint statistics as well as the structure of the connectivity. It's possible to literally obtain the map of US major highways and how busy they would be. And obviously this can be done much more refined with additional assumptions, but we've done this kind of analysis even in maritime domain, which is kind of fascinating because we typically don't tend to think of maritime domain as a network, but you can always triangulate the sea and simply make it a network and do the analysis same way as any other network. And when we do that, we find most of the major sea lanes, and this is an active area of work. And I've been working over the past couple of years, and it's been very fruitful. We don't have too much time. I'm going to quickly, this is the last topic I want to talk about. Spectral partitioning and applications to topological clustering is a very fascinating area of graph analytics. There's in particular this matrix called graph Laplacian, which is defined here, which is the degree matrix minus the adjacency matrix. Graph Laplacian on its own, one can write a book on graph Laplacian, and there are some books written actually, and I have provided some references at the end of this talk. Anything you want to know about a graph usually can be answered by the graph Laplacian, and this optimal graph partitioning is one of those examples. So let's define a cut size based on, let's say we cut a graph into two G1 and G2, two subgraphs, and we sum over all the edges crossing between these two partitions, and we call that the cut size. And if you want to minimize this cut size, it turns out the problem is reduced down to calculating this expression S transpose LS, where S is the partition assignments for the nodes. They can be 1 or minus 1s, depending on which partition a node belongs to. So the problem reduces to finding an S value that minimizes this product, S transpose LS, where L is the graph Laplacian. So solution of this can be provided by using the eigenvalue equation, because if you look at the eigenvectors of the graph Laplacian, and this is a positive semi-definite matrix, and eigenvalues of the Laplacian are all 0 and above. So the lowest eigenvalue will be 0. If you select S to be the lowest eigenvalue, you are guaranteed that result will be 0. But that's not very interesting, because picking the lowest eigenvalue corresponds to not cutting anything at all. It corresponds to putting the entire graph in one partition and nothing on the other partition. So obviously that's not the solution we are interested in. The next non-trivial partitioning of the graph that minimizes the cut size is given by the second smallest, by the eigenvector corresponding to the second smallest eigenvalue of the graph Laplacian. And that is what I show here. If you look at the second eigenvector, it's going to be something like this. And you can look for a gap in the values of the second eigenvector to assign vertices into partitions. And this is a way to optimally partition a graph. Here's an example. This is again from the student's graph. And this is what I'm showing here is the second eigenvector of the graph Laplacian. As you can see, just like in the previous plot, values of the eigenvector make a sharp transition right around the region where the optimal partitioning is. And of course, here there are some nodes that can be assigned to either partition. These are on the boundary, which is very normal. But here is the result. Oh, sorry, there's one more thing. It's possible to minimize trivial cuts by modifying this cut metric, because sometimes partitions can be very trivial, such as having one vertex in one partition and all the rest of the graph on the other. That can be addressed by a modified cut definition where we penalize small partitions. But when I run this on the students' network, the students were assigned to these two partitions. And what you see here is these icons are defined by school. And as you can see, there are only two mistakes here. These two students are part of the left school, but graph partitioning assigned them to the right school. But you cannot blame the algorithm here because essentially, I mean, this node, for example, it has just as many links on both sides and similar to this node. So this is a very good result where the optimal partitioning clearly works and gives a very informative result. And here are some other examples of the eigenvectors of the Laplacian matrix for two toy graphs. As you can see here, not only you see the transition here, but in this kind of network, you can see these multiple steps of the transition, because inside each one of these partitions, you have further partitions. But initially, when I was first studying this some years ago, I was really excited because I thought, wow, this can be used not just to divide the graph optimally, but also finding further partitions. That is still true, but it requires a few more steps actually, because here's a case where it can go wrong. If you have a graph with a total symmetry like this, optimal partitioning, for example, will give you either this or some other similar partitioning, but you're not going to get all three partitions because the partitions are on a circular sort of structure here. They are not on a straight line, kind of. Therefore, you will have to do repeated partitioning, iterative partitioning, first dividing into two and then dividing the remaining parts into two. So that is understandable, of course. So last application of this Laplacian graph partitioning is to the problem of graph data clustering, which is normally not related to graph analytics. But when you have data clustering problem, often we use things like k-means algorithm or similar things. But sometimes the problems are complicated. Like, for example, in this case, there are two rings, concentric rings. So here clusters are not defined by density, but they are defined by connectivity. So for example, these two data points are very far from each other, but they are part of the same cluster, whereas these two nodes are close to each other, but they are part of different clusters. Unlike in a typical clustering problem here, connectivity is more important. And Laplacian graph partitioning can be helpful in these kind of situations. If you take the data set and minimally link these data points to each other, and there's an art to how to do that, and that's an area of course, research. There's a lot that can be said there, but I'm going to assume you can minimally connect every node to some nearby node. Now it becomes a graph problem. You can solve it as a graph problem. And what happens is, if you turn this into a connected network, the first few eigenvectors are going to correspond to these individual components. And using those few eigenvectors, you can map these data points into a new coordinate space where each row in this eigenvector space defines the new coordinates of the data. For example, blue, green, and red dots here are mapped onto regions of the 3D space where the center of the clusters are at 1, 0, 0, 0, 1, 0, and 0, 0, 1. So this clearly separates those clusters. And now you can actually use k-means algorithm. So this is a mapping of the topologically complex structure of data into a separable representation where you can use your favorite algorithms. So basically, graph Laplacian can help with that. And in fact, it can also tell you how many clusters you have because there's a gap in the eigenvalue spectrum. When you calculate the eigenvalues of the graph Laplacian, for example, in this toy example, there are 4 clusters. You see that the first four eigenvalues are 0, and after that there's a gap. So you would know that there are 4 clusters. Of course, if you link points between these clusters, these are going to be a little bit, there's going to be noise here, but you can still look for a gap to identify optimal number of clusters. So, and here's the example from sort of 2 algorithms. Here I use k-means, which completely disregards the structure of these rings and slices the rings into 2, whereas the spectral clustering accurately identifies 2 rings as separate clusters. So this is my last slide. Graph analytics is an exciting field, and it's at the intersection of exciting fields of computer science, linear algebra, and probability statistics. And there's no shortage of interesting problems. Really, it's a fascinating field to be working in. I provided some references for those interested in exploring these topics more. And there are some sites. There's no shortage of data also, interestingly, in this area. And there are some websites. And I'm always happy to answer your questions, whether through email or later on also. And thank you for participating in this and appreciate your time. Thank you.